Yeah, so my name is Ting Fang Yen. I'm Director of Research at DataVisor. We are a Series C startup focusing on online fraud detection. And this talk is about applying deep learning to some of a new domain for deep learning, and where it's really about applying a complex model and data pipeline without big company budget and resources, but also about evaluating a model in this field, the security field, that is largely dominated by, I should say, heuristics, domain expertise, with requirements on the explainability of the results. Now, before I dive into too much details about our deep learning model, I wanted to tell you a little bit more about modern online fraud. Now, traditionally, when people hear about fraud, the first thing they think of is transaction fraud. So somebody has a stolen credit card, makes a purchase that results in chargebacks, and either the bank or the merchant takes a hit. Well, this may be the predominant fraud scenario, I'm going to say maybe 10 or 15 years ago. Today, the fraud landscape is much more diverse and complex. And this is due to the many new available features that are available in these online services and platforms we use every day. And you may even have heard about some of newer fraud attacks in the news already. So these fraud attacks are costing businesses millions of dollar losses per year, but not all of them are exploiting vulnerabilities in the service. Writing a review is a perfectly valid action on a social network, but never mind that it's a fake review somebody paid me to write. So these fraudsters are simply abusing available features that's already there for financial profit. And so to do this, all they need is to register accounts, or even better, compromise existing users. And that will give them access to everything they need on the platform in order to conduct their attacks. Now, today, online fraud is largely orchestrated by organized crime rings, controlling fake or compromised accounts en masse. The fraud economy is also highly specialized, with a market of suppliers providing services for all aspects of the fraud operation. As an example, there are people who specialize in just mass registering fake accounts, and there are people who are specialized in providing the network infrastructure for carrying out these attacks, from data center or proxy services to hide the attack origin, to redirection or other levels of obfuscation to hide the malicious content. And today, existing anti-fraud solutions typically rely on blacklists or reputation lists to block known malicious activities. Or they may have manually crafted rules to identify known attack patterns. And some of them even have labeled data and features engineered by human analysts for model training. And as a result, they often produce models or features that are very specific to a particular online service or particular data set, and may not generalize well to other attack types or to changing attack patterns. One of the more recent approaches to online fraud detection is unsupervised machine learning. And the main observation here is that fraud is done at scale, often using scripts to control these malicious accounts. And so these bot accounts, they behave very differently from that of normal users. They act in a coordinated fashion. And so by analyzing and clustering and looking at these correlated users together, we can start to see patterns emerge that were not previously visible when you view each of these users in isolation. Of course, the main benefit of unsupervised machine learning is that it does not rely on examples of known past attacks. Now, at DataVisor, we work with some of the largest internet properties across the world in different industries, including financial, e-commerce, mobile gaming, and social networks. We have a production unsupervised fraud detection system that's been running for the past 4 years or so. And it's currently processing an average of 1.2 billion application-level events and detecting millions of suspicious accounts per day. Now, as we analyze more and more data and observe more and more fraud attacks, we also notice that there's a lot of commonality in our clients' data, regardless of the industry, and a lot of commonality in the types of attacks that they face. So we started thinking whether we can leverage this combined data from our clients to improve our fraud detection capabilities. There's some data fields that are present in almost all application-level events, regardless of whether that event's a account opening, it's a login, it's some sort of payment, it's post, it's messaging, it's follow, it's like, it's level up, and gaming apps. There's some common fields across all these events. So if we were to collect the data in these common fields all together, then we can assemble an impressive database of anonymized common digital identifiers that may include IP addresses, email domains, user agent strings, device types, and phone number prefixes. Now, in addition to these digital identifiers, we can also calculate aggregated user behavior information on each of these identifiers. Now, information like, hey, when's the first time, or when's the last time that I see this identifier being used? What is the total number of users or total number of fraud users I see associated with it, maybe over some period of time in the past? What is the average daily ratio of new users I see coming from this identifier? And what's the common geographic locations that users associated with this identifier typically originate from? And many, many more like that. So we have this rich set of common digital identifiers and the user behaviors that we observe on them. And we also have this huge set of label data generated by our production online fraud detection system, the supervised fraud detection system that's been working for the past 4 years. So we have all the data, and we have some labels. And the question now is, can we find some smart algorithm that can identify the intrinsic relationships between these common identifiers and user activities? Can we generate some sort of score, whether it's a suspicious fraud score or a good user score, based on only these common fields? And not surprisingly, we turn to deep learning for this problem. Deep learning has seen a lot of success in recent years, especially in fields like image recognition, natural language processing, and for applications like AlphaGo. One of the reasons that deep learning models have been so successful is that its performance scales with the amount of data, in contrast to some of the other machine learning algorithms. And along with the success of deep learning, there's a bunch of tools and frameworks created, and often open source, to help with deep learning tasks. But even with all these tools available, if you look around and see who's really using deep learning in production, it's really the big companies with a lot of data, a lot of resources. So one of the reasons that it's more challenging for smaller startups like us to apply deep learning to our problems is often the lack of label data. Now, for us, we're lucky that we have an unsupervised fraud detection system that's been running in production. But in typical circumstances, it may be very expensive to obtain label data. Maybe you require people to label it. Maybe you can't get it on time because the labels aren't available until weeks or months later. But actually, the real hurdle to applying deep learning is actually a more technical one. It takes a lot more effort to build a production deep learning system than just training a deep learning model. So this diagram is from a 2015 NIPS paper titled "The Hidden Debt in Machine Learning Systems." So here it kind of shows like what a real deep learning data pipeline may look like in practice. And you see there's a lot of components here. There's your configuration files, there's your data processing, there's your feature extraction, analysis tools, resource process management, there's your serving infrastructure, and your monitoring system. And here, the size of the boxes in this diagram is proportional to the number of lines of code it took to develop that particular module. Now, if you take a look at the middle of this diagram, there's a really small box, a small black box. It's called ML code. And that's the core machine learning algorithm code relative to all these other components around it. And that's the real challenge for deep learning, especially for smaller startups like us. Now, of course, we know that there are a lot of tools out there that can help us. Spark is great. Spark can simplify workflows related to big data analytics. It's more like we can call it a unified engine in the sense like it's more of an end-to-end solution. So our engineers, our data scientists, they don't have to mess around with different frameworks in order to do their job. Spark can take a lot of things from loading the data to the map-reduced computations to data manipulation to data storage. Spark also has a very easy-to-use API. It does a lot of optimizations for you under the hood. and it does all the distributed system computation for you. So the users don't need a deep knowledge of distributed systems in order to use it. Now, if you really want to pick on Spark, I'm going to say the deep learning integration is still under development. And TensorFlow is another useful tool for deep learning applications, and one of the more popular ones out there. Developed by Google, TensorFlow has an extensive set of machine learning APIs that allow users to perform very detailed customizations on their machine learning algorithms. However, most of the supported processing in TensorFlow are geared toward more well-studied applications like image recognition or natural language processing. And the best supported APIs in TensorFlow are mostly written in Python, so which it creates an additional hurdle for us that want to interface with some of our existing production code that may be written in a different language. And also, TensorFlow is not an end-to-end solution yet. If you remember the diagram in the previous slide, most of the supported functionalities in TensorFlow are around that little black box in the middle, the core machine learning code. I know there are news that they will open source some of these other modules also in the future, but not all of them are available yet. Now, given the pros and cons of Spark and TensorFlow, we really want to leverage both so we can get the combination, the best of both worlds. Now, there are already some frameworks that do this. There's TensorFlow on Spark from Yahoo. There's Deep Learning Pipeline from Databricks. But again, most of these are geared toward these more well-studied applications like image processing and like natural language, image recognition and like natural language processing, and may not always suit the needs of our new deep learning application in the online fraud detection space. And just want to think through this problem a little bit more. Let's look at a typical machine learning workflow. So we divide our production machine learning workflow into the training and the serving phase. And in training time, you have some raw data, and then you derive some features from it. You pick a deep learning framework, you decide on a model, some parameters, you train the model, and then you evaluate on some validation data set. And you probably want to repeat the modeling and evaluation multiple times until your model performs good enough. And at serving time, you're deploying this model to production, where it can accept requests coming either like in batch mode or streaming mode. So you have some raw data, you apply the same transformation on it to get the derived features. You apply the model, and you get some inference results. Now, in addition to this typical workflow, there are also some other requirements that we need for our anti-fraud application. The first is that we're treating fraud detection as a classification problem, such that given a user or a transaction or some type of event, it's either good or bad. We also want to maintain some consistency across the training and the serving phase, so that we don't have to maintain two different data pipelines that do similar things. And lastly, we need to support post-inference analysis to evaluate the model's performance. And this is really because we're applying deep learning to a new domain. We don't know what model architecture to use. We don't know how to best encode our features. So we need to do a lot of iterations, and being able to analyze the results is really critical to understand when and why the model works and when and why it doesn't work. And just to elaborate a little bit more on that last point, let's say I use TensorFlow. I have a trained model here that I'm using it to serve these test instances. And so for every test instance data, can be user, can be event, I get a score indicating how likely the model thinks that this user or event is suspicious. Now, at this point, you probably want to evaluate results and use some standard machine learning metrics like plotting the RRC curve, calculating the F1 score, the area under the curve. But some complications related to the anti-fraud space, probably generalizable to other areas as well. The first is label data. Not just that labels are hard to come by, but sometimes the labels may not be binary. Let's say you have a fake account that's created just for the purpose of sending spam. Okay, that's really bad. Probably want to just terminate this account. But what if it's an account that belongs to a real user, but it's just compromised by the fraudster to do bad things? So in this case, I probably want to reset the password on this account, but probably not terminated. So these are just some examples, but you can see how fraud does not have a clear definition, and it falls along a spectrum. So if you mix everything together to train your model, it will pollute it and make it really not very useful. Another requirement is to actually explain the model decisions. And often in fraud, maybe in other areas as well, it's often not enough just to give a score. In many cases, we're actually required to give a detection reason why we, for example, rejected your credit card application. So this is really hard with deep learning, but we had to come up with some ways to measure, hey, which features are more important, contribute more to the model's decision, or some heuristics that are complementary to the model to try to explain the model's output. Also, there's slice and dice. I can talk about this in different aspects. Like one of it is in the training phase. So often we have imbalanced data sets. So that means there's a lot more examples of one class versus the other. And in fraud scenarios, it's not uncommon to have the overwhelming majority of your labels to be in the negative class. So in this case, we probably want to downsample the negative class. But there's so many ways you can try different sampling strategies. You can try different sampling ratios, and you probably want to evaluate the performance of each of them. So that's a lot of ways to slice dice your data. Another aspect of slice and dice is in evaluation. So your model may not perform uniformly across your data set. It may work really well for this particular type of activities, but not for others. So it's really important to see when it works and when it doesn't. In addition, we often have to analyze the results to understand why they are false negatives, why they're false positives, so we can actually improve the model. So all of these data analysis tasks are really critical when you're developing a model for a new application. So how do we handle some of these pain points or some of these requirements that I talk about? Well, so we want to stay in the Spark ecosystem for data preprocessing, because Spark has really good data manipulation support. So we have a feature extraction module that is shared between the training and the serving phase, so we don't have to maintain two separate pipelines and reduce the maintenance overhead. We use TensorFlow for modeling and inference. And then we come back to the Spark ecosystem to perform evaluation and post-analysis on the results, because Spark is really good for data analytics. Now, in the data preprocessing step, we leverage Spark SQL APIs to load the data into a data frame and then write a bunch of user-defined functions for feature extraction. A user-defined function, or UDF, operates on one or more columns in your input data frame, and maybe even join with another data frame to compute some value according to your customized needs. And you can think of a UDF as one feature function that would append a column to your original data frame with the computed values. So we have a set of these user-defined functions, each operating on different sets of columns in the input data to generate different features. And these user-defined functions are also used at a serving time. So this way we can have a common feature library, as we call it, that would generate these features. And output from this step is preprocessed data that's ready to give to the model. Now, to support the post-inference analysis that I mentioned, we also use Spark SQL. And for example, we have a data frame that's its test instance. It goes through the same data transformations using the user-defined functions as in the training phase. We then use TensorFlow serving for model inference. So TensorFlow serving is a standalone package. It's pretty lightweight. So it loads a pre-trained TensorFlow model into memory and also sets up a simple server that can accept requests and respond with the inference result. Now here we develop our own client to talk to the TensorFlow model. So given a test instance, it queries the model and gets the result back, and then it appends the result to the original data frame. And this is quite useful because now you have your feature vector and your model prediction all together. And if we're experimenting with different data sets, different models, and different user-defined functions, it's really useful to have the model input and model output together so you can debug and analyze the result. So that's pretty much it for how we leverage Spark and TensorFlow together for our production deep learning system. So we have this production system that takes input data from raw data from our clients, extracts some common digital information from it, adds a bunch of auto-derived features, and then outputs a fraud score according to the model. So how well does this work? Well, the first thing we tried is to look at whether the combined signal from all these digital identifiers is indeed better than just using a single dimension from a single set of common digital identifiers. Now, IP addresses, email domains, and user agent blacklists have long been used in the security community. So here we also use them for comparison. This blacklist is generated using the same data that we use to train the deep learning model, except the process is much simpler. We just calculate the number of fraudulent users over all users associated with a digital identifier, and then consider it as bad if this ratio is over 0.95, I think. Now, a user will also be classified as bad if it's associated with one of these bad identifiers. And here you can see that most of the time, these single dimensions have pretty limited precision and recall, especially compared to the combined signal from the deep learning model. We also deploy this model to select production clients. And this figure shows the detection gain over the previous production model. So here the x-axis is the gain over the previous model's results, and the y-axis is the precision of the deep learning model. Each data point corresponds to a different score threshold for the deep learning model's prediction output, ranging from 0.1 to 0.95. And you can see that in the most strict case on the upper left corner, we can get a 10% boost in detection results at 92% precision. Now, while we use all of our clients' data to train the deep learning model, we can also incorporate additional labels from a specific client in order to boost the model's performance for that particular client. And that's this experiment shown here. So we compare the number of detections from on the far left, it's the previous production model. And in the middle is the improved version with a generic deep learning model trained on all clients' data. And to the even better version on the far right, that's when the model is trained on a more biased set with a lot more examples from the target client's data, but even though with the same fields and the same features. So just to quickly summarize, we described how leveraging both Spark and TensorFlow can significantly lower the adoption bar for deep learning applications, especially when you have limited budget or are trying to apply this to a less well-studied domain. There's some lessons we took away from this. One is that feature engineering is important. This is not very surprising, but in the context of security and fraud, when you don't have a nice concept to describe the fraud, there's a lot of domain expertise and experience from human analysts that you can leverage. And there's also a lot of contextual information in the data you get that needs some transformation or some embedding for it to be more useful by the model. I also emphasized this already, but post-analysis on your results is really important. So what if your model doesn't perform well? It will probably happen. It does not perform well. So maybe this data, or maybe the set of features you're using, maybe some specifics of your testing data. And maybe it won't work for this customer, but it will work for a different one. Maybe it will work for a different fraud scenario, but not this one. So it's really important to really understand the limitations. I'm going to say the limitations of the model so you can produce defendable results, but also understand how to improve upon it. And lastly, we're really proud to have deployed the system in production and currently observing stable improvement boost over previous results. And I just want to thank my coworkers that did most of the work, but cannot be up here today with me, Arthur, Meng, Yang, Xu, Yuetong Wang, and Bodo Li. And thank you very much, and I'll be happy to take questions. Right now, we're doing in real time.
So do you have a streaming solution that connects to the Smart SQL? For what
Yes.
kind of streaming solution are you using?
What kind of streaming solution? So,
I mean, a Kafka or something like Spark streaming?
we develop our own streaming.
Okay.
So the data comes in streaming. You can compute a lot of this offline, and you can apply it to the test data, right? So,
And have you considered in this fraud detection the cost of a false negative versus a false positive and optimized your model based on the costs? There are different costs for a false positive versus a different cost for a false negative.
right.
So
Yeah, so it really depends on the application, how clients are using this data, right? So the cost for a false positive or false negative is much higher in like a financial setting versus in like a social setting, just a spam account, even though that also has a cost. But also in some cases, the cost is really hard to quantify. So okay, there's this malicious link, and it's impacting users on your platform. So how do you quantify the loss from this aspect? And so it's a little bit hard to systematically do it, but we're doing most heavily in the social space right now. So when you see a fake account, you know how many messages it has sent, and you can quantify it sort of in that sense. Hope that makes sense.
Do you have like separate model for e-commerce, retail managers, or you have single model working across them?
So like I was saying, this fraud is on the spectrum. So if it really mix everything together, it will make it perform very poorly. And I was talking about the compromised accounts versus like a real fake account, and you really can't mix these two. Especially like it's different as it's a financial case versus a social case, maybe some mobile thing.
And how do you typically deal with the class imbalance of the data? Because there will be very few frauds in your training data, right?
Yeah.
Any specific technique you employ, or how do you?
It was more like a trial and error, honestly. It really depends on the data.
but have you tried synthetic generation of data to balance the classes?
That's a big problem. How do you generate synthetic data? So because we have
Techniques.
right, because we want to leverage as much as we can the existing infrastructure we have from our online detection. So we can go back longer and get more data that way if that's what we want to do, or we can we usually downsample the negative class for that. Yes.
So when you find transfers from the generator, you are using transfer learning to generate labels.
Mm-hmm.
So when you apply transfer learning, you will find clusters or whatever. But that doesn't tell you which one is good, which one is bad. So you will still need to analyze to look into it.
No. Yeah. So the idea behind using unsupervised machine learning for fraud is it's not just one person doing fraud, right? Somebody controlling a bunch of stuff doing fraud, and so when you cluster, normal users don't form clusters. If you look at it in a way that's more context specific, but that's kind of a yeah, that's how our core company works. Yes. Sorry.
Are you using the clustering to generate features that then feed into the model? Is that how the?
Yeah, that's one of the next steps we wanted to do. Right now, we're using, like, let's say, raw data fields that's already in here and some aggregate statistics computed on top of it. But we are not yet leveraging all of the things that we could do, like the clustering information. I think registered. So.
It's great talk. I'm wondering, like the improvements compared with the previous production model. Is the previous production model also a deep learning model, or it's more like traditional machine learning model?
The previous production model is the unsupervised fraud detection. It's unsupervised, yes.
So purely based on clustering.
Yes, yes. And it has a lot more fields than what's available in the deep learning model, because it has everything like whatever the client gives us, but the deep learning model only uses the common information.
Okay. Another question is, I'm wondering if you have done comparison of the model performance
Yeah.
there is a like significant lift in performance.
Yeah, I'm sorry I didn't have a chance to show that slide. I should have. We did do that comparison, but we did it on some default settings, which probably not ideal. But if you want to make a supervised model work well, you probably have to spend a lot of time tuning the hyperparameters. And we didn't have so much time to do all that, so we tried a few different settings. Probably not ideal for that machine learning model, but we did see deep learning perform much better. To do a really systematic study, we need to spend a lot more time on it. Yes?
When you're looking at the connections across people that are colluding, have you looked at using a graph database or graph algorithms to extract those connections directly?
Our production system does not use, we have our own custom sort of graph connection. We don't use the existing graph database yet. I figure it's because when we started the company, there weren't so many tools available, so we had some custom ones, but we are looking into some of the newer technology that can help us. Yeah.
So your techniques might be state of the art, but your objective function might not be specific to the problem. For example, in the case of fraud, the company might care about dollars loss and might care about consumer satisfaction. So how does that impact your solution?
I think that comes down to the slice and dice I'm talking about. Right? You don't want to mix everything together, obviously, because there's different types of fraud. So when we do a testing, maybe for that, the client, the results I showed for that client, it's a social client. So we would find similar scenarios and similar type of data to use to train the model. Otherwise, it doesn't make sense to train on some financial transaction data. So that kind of partially answers the question, but the objective function, there's no clear definition of fraud. It also varies per platform. Maybe there's some business logic there. It's a policy violation, but not really fraud. So we have to be kind of careful, like how we use the model, what kind of data to use. Cool. Thank you very much.